Alright, let's take a minute to think about the small angle equation. This is the first equation we're going to be using in depth here in this astronomy course. So we know that theta equals 206,265 times diameter. We usually use a big D to represent diameter to keep these two D's straight. So diameter over distance. We'll use a lowercase d for distance. Before we get too far along here, though, we need to think carefully about how we measure angles. So normally we think of a circle, right? And we break up that circle all the way around into 360 degrees. But in astronomy we deal with such small angles that even a degree is really far too large. So we break a degree into even smaller things, right? So let's say this is 1 degree, that we're just looking at one little sliver of that circle. Well, that degree we break into 60 equal parts, and we call those arc minutes. Arc minutes, kind of like time, like you'd break an hour into minutes and seconds. We do the same thing with angles. So 1 degree is 60 minutes, and then we could take 1 arc minute here. If this is 1 arc minute, we'd break it into 60 arc seconds. So it's arc seconds that we deal with most often in astronomy, especially as we're looking at distant objects. And so in this equation, we're set up here to deal with arc seconds. So this is actually 206,265 arc seconds times diameter over distance. The units of diameter and distance don't matter so much as long as we always use the same units, because they'll cancel out and we'll be left just with arc seconds. So let's take a quick look at an example problem or two. First, let's look at one without really any numbers. Let's just say that I have here an observer, which I'll draw an eye looking out at the sky, and that observer is looking at an object some distance away. Okay? Now, of course, the diameter here is how big the object is, the distance is how far it is from the observer, and our angular size is the angle here that's sort of subtended by this object. Now, the question I have is, what if this object suddenly moved twice as far away? How would that impact the angular size? So if the diameter didn't change, the linear size of the object didn't change, it just moved twice as far away, right? It'd be kind of like we're multiplying our existing distance by 2. And since that's in the denominator here, right, it's a factor of 2 bigger in the denominator, which makes the angular size a factor of 2 smaller. So you can kind of see this relationship between the distance and the angular size. So our new angular size, presumably then, would be half as large as it was before. So we can do some of these kind of figuring type problems using this equation without ever really plugging any numbers in. We can also solve problems that give us actual numerical values. The textbook gives you 2 examples, one for Venus and one for the Moon, where they're actually using the diameter to find the distance with the angular size or some combination like that. But this works for basically any situation. I mean, you could think about a penny at 100 yards away. What would its angular size be? We can do those kind of calculations with this equation. This is a pretty clear example of a plug and chug type equation. When you have the values, you just throw them in and figure it out. So let's just do a quick example. Let's say I have some object which has a diameter, a linear size of 20 meters. So what is it, 60 feet? So this is a pretty big, maybe it's like a big billboard or something like that. And let's just say it's at a distance of 1,000 meters. Alright, so now we're talking about like a billboard at the distance of, what, a kilometer, so a half mile away. So we have some sense of scale of how big this would look to our eyes. But we could try to figure out what is the actual angular size. Well, to do that, we're just going to plug in these values, right? So we'd have 206,265 times the diameter, 20 meters, over the distance, 1,000 meters. Right, and we just plug this into our calculator. So this is the plug and chug, right? And we'd end up here with 4,125 arc seconds. Now that doesn't necessarily have a lot of meaning, right? I always try to set the scale here by the moon. Right, the moon is about a half of a degree, and so we could figure out how many arc seconds the moon is, right? So 1 degree equals 60 minutes, arc minutes, and there's 60 arc seconds in an arc minute. So let's see, 1 degree would be 3,600 arc seconds. So this is larger than a degree, right? So if the moon is about a half a degree, that means the moon's, well, you get a sense, right? This billboard would be maybe a little more than twice the size of the moon. Okay, so there's an example of a kind of problem that we could solve using this small angle equation.